Landing gear on airplanes isn't essential to flight. However, it is essential for smooth landing. Development of flight is one of the engineering marvels of the 20th century. However, one often overlooked facet of flight is the ability to bring the plane back down to the ground safest Triad airplane in 1911. The Triad was amphibious, so the retractable wheels were used to help it take off or land on water. By the 1930s, retractable landing gear was being developed for other aircraft models, bringing with it an increase in speed and efficiency. In fact, today, landing gear mechanisms equate to between 3 and 5% of the total weight of planes and can also take up a large percentage of the total maintenance time for airplane mechanics. The need to design landing gear with minimum weight, minimum volume, reduced life cycle costs, and short development time means that most landing gear components are also made by specialty suppliers due to the complexity and precision needed for landing gear parts. The main strut of retractable landing gear may be machined out of high-strength steel. This strut varies in size on different aircraft. It is the most important component of the landing gear. It supports all of the forces involved in the landing process. Attached to the main strut are the wheels, which in most airliners also include brakes to help slow the plane down upon landing. On retractable landing gear, the wheel assembly attaches to the main strut, which can be folded into the plane using internal hydraulic motors. There are also redundant systems and a manual release mechanism in case of emergencies. Retractable landing gear will generally be deployed at about 4 miles out from landing. The landing gear is a huge source of drag, so pilots avoid deploying too early, but they also need to have enough warning to abort the landing if there is a landing gear malfunction. But how do pilots know if their landing gear has been deployed? Pilots confirm that their landing gear is down and locked from 3 indicator lights that operate from sensors. Some planes also have a type of periscope in the cockpit that allows pilots.
Welcome to Kadam Academy YouTube channel. Friends, in the vehicle vibration, various videos are there. We have solved the various numerical on this undamped damped force vibration. Today's example is practical oriented. This is the aeroplane, and this aeroplane landing gear is there. The mass of aircraft is M, and landing gear which will be have the wheels on both sides, and inside this there is a mechanism, that is the landing gear of an airplane with the spring and damping devices to reduce the damping vibration. So what is the numerical? Landing gear of an airplane can be idealized as the spring mass damper system shown in this figure. Figure 1. If the runway surface is described as yt is equal to y0 cos of omega t. Determine the values of stiffness, that is k, and damping coefficient. We have to find out k and c, so that the amplitude of vibration of the airplane x limit to 0.1. This amplitude is x. Okay. The case of force vibration with the support excitation. Support excitation. So this is the excitation of the support. Okay. Also the excitation to the surface. So yt and xt. This yt and xt that we will find out. The value of x is given. Assume the mass of this aircraft is 2000 kg, and this y, capital Y or y0, there is this amplitude for this surface 0.2 meter, and frequency is omega 157 radians per second. So what is the solution? Given data is to us. This data is given to us. Mass of aircraft 2000 kg. Runway surface described as yt is equal to y0 y omega t, or we can write capital Y cos of omega t. Correct? Where this capital Y is equal to y0 0.2 meter. Omega is here 157 radian per second. Amplitude of vibration airplane, this is the x, capital X. Already we derived this equation. Watch the video for the force vibration for the support excitation. Force vibration, support excitation. That amplitude x we can find out by using the formula. This y square root of k square plus inside the bracket c omega bracket square upon denominator k minus under root of k minus m omega square bracket square plus I will extend this under root here c omega bracket square. So this is the formula for this case where the support and the surface both are exciting here. See here also excitation is there and here also excitation is there, both the side. I will zoom it the diagram so you can visualize the derivation. See, this is the runway, excitation here, excitation here. This is the K and this is the C. That way to find out the runway having some surface excitation. So how to find out this value K and C? By using this formula for this case. Under this case we can find out this one. So friend, let's put the values. We know the values of this x, y. Already we have written. The value of x is 0.1. We'll write here 0.1, which is equal to 0.2 square root of what is the value of k? K we don't know where to find out, plus c also we don't know where to find out. Omega is given to us into 157 radian per second is square upon square root of denominator right here k where to find out minus m is given to us 2000 into 157. Okay, so 157 is square, 157 is square and bracket square is different. See here, this square and bracket square, omega square 157 square and bracket square plus here plus what is that? C omega is how much? Omega is 157 and here is the bracket square outside. So this is the values. What we have to do here, as where the this x, capital X, this amplitude of body, and this y is the amplitude for the support. This is the amplitude for the body x, and that already were shown to you, and this y. Now we have to assume, find out this value of k and c. These two unknowns are there in this equation. So k we have to assume here for k 10 raised to 7 Newton per meter. Assume. In this case we assume k is equal to this much. Then first we have to find out c is equal to how much. C can be determined. Putting the value of k in this one, I will write again this 0.1 which is equal to here 0.2 which at the right square root k. K is how much I will consider? 10 raised to 7 into c into 157 its square upon under root of k is how much? 10 raised to 7 minus 2000 into 157 square bracket square plus C we have to find out 157 bracket square. I will extend this square root here. So this is the, I will just make a block for this one, will understood very easily. So this is the now equation. Here C is unknown, so solving this equation we can find out the value of C is equal to 124. This value is very bigger because this is the aeroplane, as this is the aircraft. Newton second meter 124,380, 1,24,380. So stiffness we are considering 10⁷ Newton per meter, and damping coefficient is this much. Friend, these are the two solutions we have found out. Okay. So if you are not subscribed my channel for more updated video, please watch my channel Kadam Academy. Thank you very much.